All right, so this is section 14.6, part B, video number 1. This will definitely be at least a 2 video lesson, hopefully not 3. We're still talking about directional derivatives and the gradient vector. So there's a couple of questions to ask here. So there's specifically 2 questions that we want to answer. 2 questions. Now that we kind of know how to find the directional derivative and the gradient vector, first question is, in what direction is the slope the greatest? So in what direction is the slope the greatest? And the second question would be, what is that slope? So again, you could definitely think of this as, you got some, I'm not going to draw the whole 3-dimensional shape here or whatever, but, you got some kind of a surface which is floating up here. And you could have, something like that, and then something like this. You got these different curves, and you're standing right here at this one particular point. Well, you've got all different kind of possible slopes that come off of this thing. Because you could have a slope which goes in, let's use this color. You could have a slope which goes in this direction. You could have one that's going in this direction, this direction, this direction, and then you could have every possible direction also in between. So you can have a slope going there, a slope coming out that way, that way. So if you're standing at that point, what would be the greatest slope? And remember, the slope here in 3 dimensions is the change of z over top of, and there's no short way to write this, the unit traveled in the direction of a unit vector. Unit traveled in the direction of a unit vector. We'll just call it u. So that's how you define slope. Basically, how is the z changing over whatever direction that we have for our unit vector? So our goal here is to maximize our directional derivative at some value ab, whatever that is. So let's recall, this is actually relatively easy to figure out. Let's recall what the definition or the mathematical formula for our directional derivative is. The directional derivative in the direction of u at some point ab is the gradient, which remember is just the partials, but we're going to evaluate those at our point ab, dotted with the unit vector. Well, if we remember, we had a property a long time ago that says if I have the dot product of 2 things, that is the same thing as the magnitude of the first one times the magnitude of the second one times the cosine of the angle in between. Okay, that's the old dot product property that we used way back in our first chapter that we dealt with here. So it's the magnitude of the gradient times the magnitude of the unit vector times the cosine of the angle in between. So the good thing is we know what the magnitude of a unit vector is because a unit vector literally has a length of 1. That's why they call it a unit vector. So that's 1. So really what we have here is that our dot product or our directional derivative is the magnitude of the gradient times the cosine of the angle in between. The magnitude of the gradient is just going to end up being a constant of some kind, which really tells us that the cosine of theta is going to be at its maximum. So this will be at its maximum. Well, cosine bounces on back and forth between -1 and 1. So whatever gives cosine the value of 1. So that would be when theta equals 0. So when theta equals 0, we know that cosine is at its maximum, which is going to make this directional derivative its highest possible value. So when theta is 0, we're going to have a maximum. So we ask 2 questions, we'll have 2 answers. So the first one is that the largest or maximum, the largest directional derivative will ever be is the magnitude of the gradient. And the second one is that theta equaling 0 means that the unit vector is in the same direction as the gradient. I think I actually answered the questions backwards. I actually think that's the answer to number 2, and that's the answer to number 1. I think I answered it backwards. So the largest that the directional derivative is ever going to be is simply going to be the magnitude of the gradient. And when theta equals 0, that's going to be the maximum of the directional derivative. And if theta equals 0, that means that the unit vector is in the same direction as the gradient, because if I have a 0 angle, it's going in the same direction as the gradient vector. And that's it. Let's put it into use. So let's find the maximum rate of change of f at a given point and the direction in which it occurs. We're given the function f of xy equals y squared over x, and we want to do this at the point 2, 4. So we could obviously guess. So we could guess what the unit vector is going to be. So maybe we could try the unit vector being the vector 1, 0. So we're going to do something with respect to the x-axis. Or maybe we want to go with something in the negative direction of the x-axis. Or, maybe we don't want to go in the direction of the x or y axis at all. Maybe we want to go at a 45-degree angle, which would be 1 over root 2, 1 over root 2. Notice that they are unit vectors. Or maybe we do want to go in the direction of the y-axis. Again, these are all just guesses, and we could keep guessing forever and try and figure it out. So if I was to use those guesses, that would say that the directional derivative of f, well, so for the first one, we would need to find, well, first of all, we do need to find the gradient. So let's go ahead and do that first. So we'll need the gradient vector. Let's go ahead and put that in orange. So the gradient vector is the partials. So the derivative of y squared over x with respect to x. So that's going to be basically y squared x to the negative 1. So that'll be negative y squared over x squared. Okay, that's the partial with respect to x. The partial with respect to y is a little bit easier. That's just 2y over x, because x is treated as a constant. We would need the gradient evaluated at our point 2, 4. So let's see, if we plug 4 in for y, we're going to get negative 16 over 4, which is negative 4. And then we're going to get 8 over 2, which is positive 4. So if we want to find the directional derivative with respect to u1 here, it would be, remember that the directional derivative is the gradient dotted with the unit vector. So we would dot this one with this one, and that would give us 4. If we did it with respect to u2, that would give us also 4. With respect to u3, that's going to be negative 4 over root 2 plus 4 over root 2. Well, that's 0. With respect to u4, 0 and negative 4, so that's negative 4. And, maybe one of these is correct. Maybe one of them is not. So the only real way to figure this out is to go back to what we said on the previous page, was that in order to do this, we know that the greatest slope is going to be in the direction of the unit vector. So we can find the unit vector, because what we need to do, first of all, is we need to find the magnitude, because that is going to be your greatest slope. So we need to find the magnitude of the gradient, which is going to be the square root of 16 plus 16, square root of 32. But that can be simplified because 16 goes into that, so it's going to be 4 root 2. So that's the magnitude of the gradient. If I want to create the unit vector that this thing is going to be in the direction of, it's just going to be the gradient vector divided by its magnitude. That's a unit vector, right? Take a vector divided by its magnitude, you get a unit vector. So we're going to get negative 4 over 4 root 2 and 4 over 4 root 2. And that's going to simplify, because the 4's are going to go away, to negative 1 over root 2 and 1 over root 2. So we were kind of on the right track with our guesses there. It's just we didn't have the correct x value. It's actually going in the opposite direction of the x. But this right here is actually going to be the direction. Now, if we want to double check, because we've actually already found the greatest slope, which is going to be 4 root 2, but if we wanted to double check it, we could, because we know that the directional derivative is going to be the gradient dotted with the unit vector. Which would give us positive 4 over root 2 plus 4 over root 2, which is the same thing as 8 over root 2. Rationalizing that, you would get 8 root 2 over 2, which simplifies to 4 root 2. So this does check out. Okay, we didn't have to do that part right there, because we actually found it right here, and we found it right here. And obviously these were close. This stuff over here, it was close, but it wasn't what we were looking for. The first one gave us a magnitude of 4, the next one 4. Technically the magnitude on the bottom one was 4 and 0, but we didn't find one with 4 root 2 until we actually did it the other way. So I did a lot of extra work there that doesn't need to be done, but all you have to do is you have to find the magnitude of the gradient, and then you can find the unit vector that gives you the direction. That's it. So really just the 2 check mark steps on the top there with the boxes. Oh, that's all the problem there's for that one. Okay, so number 2. Suppose that over a certain region of space, the electrical potential V is given by V of xyz equals 5x squared minus 3xy plus xyz. Okay, so now we're dealing with a little bit of physics here. Find the rate of change of the potential at the point 3, 4, 5 in the direction of the vector I plus j plus k. In which directions does V change most rapidly at P, and what is the maximum rate of change at P? So it's pretty much the same idea. Now the first part is literally just asking us to find the directional derivative. So part A says find the directional derivative, and again we know that the directional derivative of f is going to be the gradient of f dotted with a unit vector. Well, they gave us a v vector. It's not a unit vector, so we can create the unit vector. So v is 1, 1, 1. Something's not right. Oh, there's a typo. That's what it is. So I knew that wasn't right. This should be I plus j minus k. Sorry. Which is going to make that a minus 1. Okay, so change that to I plus j minus k. Okay, so now we can create our unit vector. Our unit vector is going to be the v vector divided by the magnitude. The magnitude of v is going to be the square root of 3, right? 1 squared plus 1 squared plus 1 squared is 3. So take the square root. So what we're going to get is 1 over root 3 times 1, 1, negative 1. That's our unit vector. Our gradient is the partials. So first of all, the partial of this thing with respect to x is going to be 10x minus 3y plus yz. Then the partial with respect to y, the 5x squared goes away, negative 3x plus xz. And then the partial with respect to z, the first two terms go away, and that leaves you with xy. And then we need the gradient evaluated at 3, 4, 5. So let's see, plugging in 3, 4, 5. So that's going to be 30 minus 12 is 18, plus 20 should be 38. Plugging it into the second component, so that's going to be negative 9 plus x times z is going to be 15. So negative 9 and 15 is 6. And then xy is 12. So there's our gradient evaluated at our point. We have our unit vector. We can find the directional derivative, which is going to be 1 over root 3 times, oops, not a vector, times 38 plus 6 minus 12. So 38 plus 6 is 44, minus 12 should be 32. So we're going to get 32 over root 3. And that's the directional derivative in the direction of I plus j minus k. Part B wants us to figure out in which direction does v change most rapidly. Or basically, it wants us to figure out what's the direction, what's the maximum, where does, the maximum change occur, which direction? Well, we already said in the previous part that it's going to occur in the direction of the gradient. So we already have the answer. It's going to occur in the direction of 38, 6, 12. And then what is that maximum? Well, that's going to be the magnitude of the gradient, which is going to be the square root of 38 squared plus 6 squared plus 12 squared. I have no idea what 38 squared is, so I'm going to have to plug that into a calculator. Okay, so I'm getting, when I simplify this, 2 times the square root of 406. Okay, you don't really have to simplify it to that, but that's what I got. All right, so there we go. All right, I think we're going to do one more, and then we're going to jump into some stuff about tangent planes with all this. All right, so we want to find all the points at which the direction of the fastest change of the function f of xy equals x squared plus y squared minus 2x minus 4y is I plus j. So we're telling you that this time the specific direction that we're interested in is in the direction of the vector 1, 1, or I plus j. But we want to know what are all the points that that's going to be the case. So there's not going to be an infinite, like you can't, there's not an infinite number of equations that this will work for. Well, that's not true. There actually is in this case. But there's a list of points. So it's not every possible point on a function. It's what are all the points on that function that this is going to be true. That was probably a little confusing, so I apologize. Well, in order to do it one way or the other, we still need the gradient. And the gradient in this case is 2x minus 2 and 2y minus 4. we need to evaluate the gradient at our points A and B. We don't know what those points are. It's kind of what we're solving for. So if I were simply to plug A in for X, I would get 2A minus 2, and plug B in for Y, you get 2B minus 4. Well, that has to equal some values, and we'll just call them C's for right now. Some C value. Now the question is, how do I know specifically that that's going to be C and C? Well, this is how we know. Whatever the direction is, and I don't know exactly what this is going to be, so I'm just kind of drawing it out this way. If this is the direction of our gradient vector, then this is also the direction of our gradient vector. Then this is also the direction of our gradient vector. So basically, anything along that specific line is going to add up. So whatever these values are, they're going to be the same value. The C value is going to be the same. So what I can do is I can take 2A minus 2 and set it equal to C. Oh, and how did I know that, by the way, this is not drawn very well. How did I know that? Because it's got to be in the direction of I plus j, which is a vector of 1 and 1, 1 and 1. I did not do a very good job drawing this thing with respect to keeping the intervals correct. It doesn't look right, but and then down here we're going to have 2b minus 4 also equals c. Well, this is basically two equations that equal the same thing, so we can set them equal to each other and solve. So what I get is that 2a minus 2 equals 2b minus 4, because they have to equal the same c value. Well, if I want to, I can divide in a 2 out of everything. So a minus 1 equals b minus 2. And it doesn't really matter here. You can solve for a or you can solve for b. It's not really going to make any difference. I'll solve it for b. I'm just going to add 2 to both sides. So we get that a plus 1 equals b. So then remember that a represented our x value right here. A represented our x value. So any point that I want would take on this form. A, that's the x value, and b represents the y value, but b is equal to a plus 1, so a plus 1. Or I could say anything that is on this line. Y equals, don't forget that in this case, a is x, and y is a plus 1. So if I simply replace the a with x, my y value is x plus 1. So anything along that line. Okay, not exactly the easiest problem to see, but hopefully it kind of makes sense. All right, I will come back with a second video and we will talk about some shortcuts and some kind of interesting things here with tangent planes.